So, today's topic is law of chemical equilibrium and equilibrium constant. So, according to law of mass action which is applied to a reversible reaction, let the reaction be A plus B gives C plus D. This is the reaction. From this we are writing a law of mass action. R is equal to some K into A into B. A and B are the concentration of reactants, reacting species, and K is the proportionality constant. Okay, so from this equation we are deriving a mathematical expression which is known as law of chemical equilibrium. Okay, now how can we do that? So this A and B gives C plus D. This is a forward reaction and this is the backward reaction. So instead of R for forward reaction we can write RF. RF is equal to KF into A into B. Similarly, for the reverse reaction is backward reaction. So RB is equal to KB into C into D. Okay, this is the reaction. At equilibrium what happens? RF will be equal to RB. Okay, or we can write RF into A into B will be equal to KB into C into D. Okay, or KF by KB equals C into D by A into B. Okay, so this is the equilibrium constant. So instead of that we can write the concentration constant, equilibrium constant. In the case of concentration we can write Kc into C into D. Now the reversible equation contains the coefficients A, B, C, D. Okay, that is A plus, this is the equation, gives CC plus DD. In the case of what will be Kc? Kc will be equal to C raised to C into D raised to D by A raised to A into B raised to B. These are the coefficients of the equation, and this equation is called, this mathematical expression is called as law of chemical equilibrium. Okay, law of chemical equilibrium. Now this Kc is also at equilibrium. We can also call them as concentration coefficient. Concentration quotient. Okay, concentration quotient we can write instead of K. So K will be equal to, Q will be equal to K. Instead of concentration quotient we can write Q. Q will be equal to K, or Q will be equal to this expression C raised to C into D raised to D by A raised to A into B raised to B. Now we know Kc is for the equilibrium constant. If we reverse the equation, what happens? Instead of Kc we can write K dash C. Okay. Now in the case of gaseous reactions what happens? Gaseous reactions, instead of concentration we are writing the partial pressure. So Kp is the equilibrium constant. Okay, which will be equal to Pc raised to C, where Pc is the partial pressure of C, then Pd raised to D, partial pressure of D, then Pa raised to A, Pb raised to B. Okay, this will be the equation. In the case of gaseous reaction, instead of concentration we are writing partial pressure. Okay, relation between Kp and Kc. Kp and Kc. Kp is the is the equilibrium constant for gaseous reactions, and Kc the concentration for the concentration equilibrium constant for the concentration terms. Now we know the equation is AA plus BB gives CC plus DD. Okay, so Kc is equal to C raised to C, D raised to D by A raised to A, B raised to B, and Kp is equal to Pc raised to C, Pd raised to D by Pa raised to A, Pb raised to B. Okay. So for ideal gases, we know PV equal nRT or P is equal to N by V RT, or this is equal to CRT. N by V is the concentration. Okay, CRT. So PA will be equal to concentration of A into RT. So similarly for all the other, PB will be equal to concentration of B into RT. PC will be equal to concentration of C into RT. PD is equal to concentration of D into RT. Okay. Now, what happens? Kp will be equal to Pc raised to C. So, what we can write? CRT raised to C, then concentration of DRT raised to D. Now, RT raised to ART raised to A, concentration of B into RT raised to B. Okay, so like this. Now, what happens? This is equal to C raised to C into D raised to D, RT raised to C plus D. We can write like this. Similarly, here also, concentration of A raised to A into P raised to B into RT raised to A plus B. Okay. Now, instead of this, we can write Kc. Okay. So, Kp will be equal to Kc into RT raised to C plus D by RT raised to A plus B. Or this is equal to Kc into RT raised to C plus D minus A plus B. Okay. C plus D minus A plus B means that is the change in the number of moles of the products and the reactants. Okay. So this can be written as Kc into RT raised to delta N, where delta N is equal to C plus D minus A plus B. This is the change in number of moles of the products and the reactants. Okay. So this is the equation. Okay. Now, if delta N is equal to 0, that is change in the number of moles will be equal to 0, what happens? Kp will be equal to Kc. Okay. So if delta N is equal to 0, Kp will be equal to Kc. Next, characteristics of equilibrium constant. Characteristics of equilibrium constant. First point, we know Kc or Kp are the equilibrium constant for concentration and partial pressure. Now, if we reverse the equation, their constant becomes K dash C and K dash P. So, if Kc is 10, what will be K dash C? K dash C will be equal to 1 by 10. Like this, we can find the equilibrium constant of the new equations. Okay, if we reverse the equation. Next, second point. If we consider the equation 2SO2 plus O2 gives 2SO3. And equilibrium constant is 25. Okay. In this equation, if we divide the whole equation by 2, so the new equation becomes SO2 plus half O2 gives SO3. In this case, what will be the equilibrium constant of this new equation? Kc will be equal to root 25. Square root of this constant. Like this, we can find the equilibrium constant of the new equation. Now, next third point. Take another equation, half N2 plus half O2. Half N2 plus half O2 gives NO. And the equilibrium constant is Kc is 5. Okay, Kc is 5. In this equation, what happens? If we multiply this equation by 2 or we double the equation, what happens? N2 plus O2 gives 2NO. In this case, what will be the new equilibrium constant? New equilibrium constant will be 5 square or 25. Okay, like this we can find the the equilibrium constant of new equation. Instead of 2, if there is n times, then Kc will be equal to raised to n. Like this we can find the equilibrium constant of the new equation. Okay. Now, if we return an equation in more than one step, okay, and the equilibrium constant for different steps are K1, K2, K3, etc. Now, what will be the equilibrium constant of the whole equation? If the equation is written in more than one step, the equilibrium constant of this equation Kc will be equal to K1 into K2 into K3, like this. Okay. Now, next, fifth point. Do not include concentration terms for pure solids and pure liquids. So, while we are writing the equilibrium constant, we are considering only about gaseous substances. So, for example, equation C solid, H2 gas gives CO gas and plus H2 gas. This equation. Here the carbon is solid. So no need to write the concentration of pure solid. Okay. So Kc will be equal to concentration of CO into H2 by H2. Okay. Like this. Now, next one, sixth point, one half equation. One half equation. This one half equation. One half equation is log to the base 10 K2 by K1 equals delta H by 2.303 R into 1 by T1 minus 1 by T2. T1 and T2 are the temperatures of two different equations, and their equilibrium constants are K2 and K1. For T1 temperature, the equilibrium constant is K1, T2 temperature equilibrium constant is T2, and delta H is heat of reaction. Delta H is heat of reaction. R is a constant called gas constant. Okay. Now, seventh point, last point. The value of equilibrium constant is not affected by the addition of catalyst. Okay. Equilibrium constant is not affected by the addition of catalyst. Addition of catalyst. So, if we are adding a catalyst, what happens? It increases the speed of the forward reaction and backward reaction to the same extent. So, there will not be any change in the equilibrium constant. Okay, but only the speed of the reaction is increased, of backward and forward reaction, which will increase at the same extent. Okay, this much about the characteristics of equilibrium constant.